Hi there, this is Professor Bacon. I wanted to take this opportunity to perhaps go through a few problems with you from Chapter 1, 2, and 3, just so you have some ideas as to how I might approach some of these problems. I want to get a blank slide up here for my PowerPoint. Okay, so we can use that to work from. All right, see if we can drag that over here. Okay. All right. In Chapter 1, I think the only item that I might notice that people have struggled with has been the question that asks about how much time it would take to double the number of cars produced for given a particular percentage increase. Let me pull that problem up here and get the exact numbers that I put down there. So it looked like problem number 7. So let's look here. Let's insert some text in here. Okay. We have 13 years during which time 6.7% increase per year was the rate of growth. Of automobiles in the U.S. Okay, so how do we approach that? Well, let's take a look here. Let me well, what if we start out and ask the question? Really, what we're looking for is the equation that says if we start with 1, if we let n equals 1 be our starting number, because it doesn't really matter, does it? You could say 100, you could say 100,000, whatever it is. We want it to go from that starting unit at time t equals 0, and then to subsequently it becomes n equals 2 at some time t that we're looking for. Okay, and we'll designate x. X will be our interest rate, and 6.7% interest rate is 0.067, isn't it? Okay, so what does that mean? Okay, well, after 1 year, when t equals 1, so let's write that down, then the number will be the number you start with at the beginning of that year, which is 1, plus the interest rate, 0.067, won't it? Okay, or to write that generically, we just say 1 plus x. At t equals 2 years, then the number we'll get at the end of 2 years is the number we have at the start of that second year, right, after 1 year. So then n equals 1 plus x, that's what we started with the year, plus the percentage increase on that starting amount. So that means we're going to multiply x times 1 plus x. Okay? So the first part of this term, I don't know if you can see that, if I highlight the first part, 1 plus x is what we started the second year with, and then at the end of the second year, that starting value 1 plus x was increased by the percentage x. Well, notice what you have there. You have 1 plus x, which you can factor out, which leaves you, again, 1 plus x. So this is actually, parentheses, 1 plus x raised to the second power. Where's my superscript? There it is. 2. 1 plus x squared. Okay. So at the end of 1 year, it's 1 plus x. The end of 2 years is 1 plus x squared. Okay, so we keep going on and on. T equals, well, notice what's going on here. 1 plus x is the same as writing that as, let's write that up there, 1 parentheses, 1 plus x raised to the first power. All right, let's put a superscript on there, okay. Okay, so after year 1, the term 1 plus x is raised to the 1 power. After year 2, the term 1 plus x is raised to the 2 power. So after year whatever, let's say year 10, then the number would be parentheses 1 plus x raised to the 10th power, wouldn't it? And that would tell us how many vehicles were produced based on a 6.7, or that's our x value, that percentage increase in a 10-year cycle. Well, how many do we want? Right? How many do we want? Well, we want to go from 1 at time 0 to 2 at some time that we don't know what it is, right? So in essence, the n we're looking for, n, will be, I still want capital N there, come on you, n will be 2, right? That's our ending value, a doubling of the original value. So we're going to substitute that n in our equation, parentheses, 2 equals 1 plus, 2 equals, whoa, what happened to my thing there? 2 equals, parentheses, 1 plus x raised to the number of times it takes to go from 1 to 2 with a percentage increase of x. So the superscript here would be the unknown. This is the thing we're looking for. How many times do we have to cycle this process so that the 1 goes to 2? So I don't know what we want to call this. We'll just call it, z. Okay, we're looking for z. What is the value of z that makes the equation 1 plus x equal to, raised to the z equal to 2? Right. So we know what x is. Oops. Oh, don't do that. We don't want the superscript anymore, do we? Okay. So we know we've got equation 2 equals, parentheses, 1 plus 0.067, that was our x value, our percent increase, raised to the z power. Okay, raised to the z power. Okay, whoop, I can take off that superscript. Okay. Increase that a little bit up here, okay. Make that a little darker. All right. So there we go. 2 equals 1 plus 0.067 raised to the z power. That superscript there is z. So I'm going to leave the rest to you on this one. That's the equation that will get you from unit of automobiles 1 to 2 in a certain time span. The z is the thing we're looking for. How many times do we have to repeat this to get to double from 1 to 2 at a 6.7% increase. Okay? All right, let's go on to chapter 2 in particular. Let me scroll down here in my text and find chapter 2. Sometimes the numbering in the book gets altered slightly as a result of additions and new things. So you might notice that while the assignment indicated pages 41 to 42 to 47, in the actual book you'll see that the problems start on page 41 with the particular problem that talks about the Leaning Tower of Pisa. The problem, the height of the Leaning Tower of Pisa is 54.6 meters, and how fast will lead weight dropped from the tower be moving when it strikes the ground, and how long does that take, right? So if you were to scroll back a couple of pages to the various formulas that are discussed in this chapter, you will note, and this should be on page 40, there's a list of formulas showing you how to find x given v0 and v and a and t and so forth. Okay. So I'll refer you to those formulas on page 40. You'll notice that the ones I just copied in here are not properly subscripted or superscripted. This part right here, AV, should be a subscript on V, and here's an A squared, that should be a superscript on T. So the format just didn't copy over the proper super and subscripts. Anyway, you know where the right formulas are and what they look like. I just want to give you some guidance here. Now, consider this particular problem. What do we know? Can we label? Looking at our formula sheet down here at the bottom, we have symbols for things. Remember, x is a distance, t is a time, v is a velocity, and a is acceleration. So if we consider this problem, this is a one-dimensional problem. The object is being dropped and it falls straight down. So we have a choice. Where do we put our origin of our coordinate system? It'd be like asking the question, if I have a ruler, okay, designating what are we going to designate as the origin, the starting point? Okay, in this case, you've got a vertical problem, so we have two choices here. We could designate the ground as a 0 point, or we could designate where the object starts and designate that as our 0 point. It won't make any difference in the time it takes, and it's only going to make a difference in the direction of the velocity. Well, here, let's start this way. I'm going to designate the ground. It just seems more logical to designate the ground as our starting point. So that means that our origin on the ground, so our starting value of the object is 54.6, isn't it? So let's call that x0 equals 54.6. Okay. So what is x final? What is x? X without a subscript, okay, in this first equation here, for instance, the value of x is referring to its position at the time t that we're interested in. And we're interested in where is it, at time t, it's going to hit the ground, obviously, so x will be on the ground, so that its final position, x, we can designate as 0. What else do we know? If we look at our formulas down here, for example, let me subscript that average term. Here in V average we have a V0 and a V. So V0 is our original and V is our final. Now final is just the instant it strikes the ground, so it's not 0 because it's resting on the ground. The final velocity is how fast is it going when it strikes the ground. Okay, V0 is how fast is it going when it starts to fall. Okay, well that means obviously V0 equals 0, right? And V final we don't really know. Actually we're looking for that, and right up here it says how fast is it moving when it strikes the ground. Oh, okay, that's cool. All right, so I might put that down as V equals question mark, just to indicate that it's something I'm looking for. What is the acceleration? Okay. Well, I don't really want capital A there, but that's what this program's thing's doing, isn't it? Okay. A equals. Well, because we have a one-dimensional problem here, and we've designated the ground as 0 and the top of the tower is 54.6, we've inherently said that the upward direction is positive, haven't we? Yeah. Okay, because we're going positive up. So acceleration of gravity being downward is directed in the opposite direction. So I'm going to give that a minus 9.8. Now I'm leaving out the units on this, you know, the proper units in meters and meters per second and meters per second squared. Okay, and do we know the time? Well, the answer is no, we don't know the time, but that's one of the things we're looking for t. Okay. All right, so now if you were to take these things that you know and place them into these equations, you would have certain quantities that are unknown, in particular V and T, wouldn't you? Because you know what the X's are, you know what V0 is, and you know what A is. So to pick the right equation, you just look at what is it we're looking to solve for. Well, we already determined that, didn't we? We found here that we want to solve for V and we want to solve for T, right? Okay. Well, let's pick an equation that has T in it, for instance. I'm going to highlight this one right down here. Down there, let's change that to, I don't know, green's not very good, is it? Let's change that to red. Highlight that equation, because if we plug in x and x0 into that, we've got 0 equals 54.6, v0 is 0, so that term drops out, and 1/2 a negative 9.8 t squared. Oh, that would allow us to leave, the only thing we don't know in there is t, and that's what we're solving for. So once we solve that equation, okay, once we solve that equation, then we've answered the question, what is the time? Then we can come back to, what about the one right before it, equation right before it? Since we found the time, we could then solve that one for the velocity at that time. Okay, so that's not too bad. Let's see what else. I'm kind of done with that problem. Let's take a look at the next problem in that is, man throws a baseball straight up at 25, how high will it rise? Aren't we doing exactly the same thing, except we're moving in the opposite direction as we were in the previous problem? Yeah, so you're throwing it up, so it's got a positive starting velocity instead of a 0 velocity. But it rises up, and at the point of its maximum height, it has no speed. Right? So if V0 is 25, then V at the high point is 0. Because if it still had velocity, it would still be rising. Right? Sure. Okay. So we know what our two V's are in that problem. We know what our acceleration is. It's negative 9.8. And we're finding, in this case, the time and the distance the value of x. Okay. All right. The problem on page 44, which is labeled problem 4, states the following. And I'll just insert it in here. Particle moves in a straight line. The position of the particle is given by the equation 5t, or what? 5t minus 20t squared. Okay. I'm going to come back here and grab one of this previous equation and bring it over to the next slide, because you will, I hope, begin to immediately see some connection here. Here, let's slide this down so it's kind of underneath the other one. Okay. All right. Okay. Well, anyway, all right. Demonstrations, card. I'm just looking for something. I don't know why. Oh, here we are. Here's what I want. I want to show you that clearly in this problem, if there's a 5, the 5t is going to correspond to that term VOT, right? And the minus 20t squared is going to correspond to that term. So we could immediately do the following. And notice that there's no x0 term showing up in the actual equation, so we can immediately identify x0 is 0 and v0 is 5 and a is, well, what's a? Well, if minus 20 is 1/2 of a, then a is minus 40, right? So we've immediately identified by correspondence with this generic equation, the specific equation gives us this particular information here. Okay. All right. So when you come back to the problem in hand, is the particle accelerating? You can say, well, sure, there's a value of a, but it's negative, so we're slowing down. What is the value? You've got it, minus 40. What's the initial velocity? It's 5. Starting point is 0. Okay. Now the questions that really matter. What time does the particle return to its starting point? You might say, what does that mean? Well, think about it. This equation up here describes a particle which is moving with an initial velocity and an acceleration. But it's slowing down because it's got a negative acceleration, right? Okay, so it's moving with a positive velocity but a negative acceleration, so it's slowing down. So it's going to slow down and slow down. Finally, it's going to stop, and then it's going to start going the other way because the acceleration is still there. The acceleration is still in the negative direction. So the positive velocity gets reduced and reduced to down to 0, and then it turns around and goes the other way. Right? So at what time does a particle return to its starting point? Okay, so we know at t equals 0, the particle's at 0. So when is it again at x equals 0? Right? There's a solution to this equation, which you can find by factoring that equation, and the factor, you're factoring a quadratic equation. Factoring that equation will give you two solutions. One is t equals 0. The other one is the time it returns back to x equals 0. Okay? And then the second part, what is the maximum distance the particle had from the starting point? Well, you know that the maximum distance will occur when the velocity is 0. So maybe here, let's grab this equation from the previous slide, bring it over here, and paste it in. Okay. Right. Now, we know the acceleration is minus 40. We know that the x0 is 0. If we plug in v equals 0, we're saying that's the point x where the velocity is 0, given its initial velocity is 5 and its acceleration is minus 40. So we could solve that equation for the position x when the velocity is 0. All right. Let's grab a new slide.